All right, now we continue with chapter 2, where we learn about gradient descent. Um, so uh, we haven't really talked about how we set the weights rigorously for a perceptron. I just gave you this big idea that there's some weights that will divide the data correctly, and there's some range of these weights that will work. But how do we do it systematically? Uh, so it turns out there's a very simple algorithm, um, and we're going to describe it qualitatively now, and then in a few slides you'll see how it comes directly a bit more formally from gradient descent. Um, so the algorithm for adjusting the weight to the perceptron is, let's say you have the desired output. Oops. And that's y. Remember, this is the gold standard output, um, not not the actual output of your function. So you have x naught, which is the bias term, and what you do is you're going to take your desired output, and you can take the learning rate, and this is a constant, and you choose this constant. Uh, you'll start to get a feel for you know when you need a faster learning rate, when you need a slower learning rate. But the point is that you choose this, and then you're going to need your inputs, your x sub i's, right? And so you're going to add to your w's. Let's say you start with w's, initialize them all to zeros, right? So if you have a y that's positive and you have a learning that's constant, and we're always going to take the learning rate to be positive as well, or not as well, but we're always going to take the learning rate to be positive. And then you have some input. Let's say that one's positive. So all these are positive numbers. That means you're going to add this quantity, this product, to w sub I. You're going to add a positive number to that w sub I. And we think about it, that should make sense to you, because if you want the output to be a +1 and your x's are positive, then what you want is w1 to be more positive, right? Because whatever step you are in the training process, maybe w sub I is currently 0 or even negative, right? So you want it to come up and become more positive, right? On the other hand, if your y, let's say your y is negative, then it makes sense for your w to be more negative, right? So you subtract a little bit from it. So let's say assuming of course that your x is positive. So let's say your x is positive and your y is negative, then you're going to want this w to help you get to that negative y. So you want the w to be negative, right? Same thing if your x is negative but your y is negative. You're going to want this thing to be a negative number that gets added to your wi. And lastly, if both y and x are negative, then you want w to be positive, right? Because you don't want w to change the sign of your wx. Right. So that should make a little bit of intuitive sense, but it probably sounds a little bit hand wavy at this point. So let's get into what gradient descent and what it does for us. So gradient descent just kind of mimics the process of, let's say you have a marble in a bowl, and you just put it somewhere in the bowl, but not at the very bottom, and you let it roll around until it hits the bottom. So what it's going to do is that if it's high up on the bowl, it's going to get accelerated more towards the center. And if it's already close to the center, maybe it'll just kind of roll around a little bit and finally settle to the bottom. So that's not exactly how it works because of the difference between acceleration and velocity, but we don't need to get into that. The point is that let's say you want to minimize y, so you want to find the x's that minimize y, and you don't initially know which x that's going to be, so you just choose something. Let's say you chose this x. Your algorithm is going to be, okay, compute the slope here, and then I go, since it's curving down towards the left, I go to the left a distance that's proportional to that slope, right? So if I have a slight higher slope, I'm going to move more, and if I have a shallower slope, I'm going to move less, right? So here the slope is relatively steep, so I'm going to draw it, relatively longer, and that means that my next guess at x is going to be here, where that arrow ended, right? And then I'm going to evaluate my slope again, and now the slope is less steep, so I'm going to go a little bit less distance now, and that'll be my next try. And I keep doing this until I hit the bottom. And it's actually very likely that that'll overshoot and have to come back and kind of zigzag a little bit until I finally converge. Okay. So notation, derivative of y with respect to x, which is the slope. You can express it like this. You can also express it as this prime means the derivative of this function f with respect to x, or you can be even more compact and just say y prime. That means the derivative of y with respect to its argument. Okay. So that was for the one-dimensional case, but in machine learning, you're typically going to be multi-dimensional. It could be even millions of dimensions. So what do we do then? Well, then we just generalize that, and we have to use partial derivatives. And so the partial derivative just means that you're going to take the derivative of your function with respect to x naught, for example, assuming that everything else is constant. In other words, assuming that x1 does not depend on x naught, x2 does not depend on x naught, and so on. So let's say your function just happens to be ax naught plus bx1, and you want this d partial y partial x naught. That means that you're going to assume this thing is a constant, and so that just derivative of that with respect to x naught just 0, and then derivative a times x naught. Take that derivative of that with respect to x naught. This x naught, of course, just becomes unity, and so it's left with a. So partial y partial x naught is just a, and partial y partial x1 is just b in this case, right? So the gradient, this is a gradient symbol, it's just a vector of that has components partial y partial x naught, partial y partial x1, etc., all the way to partial y partial xn. And so in this case, that's just a and b, right? So this is so let's say it's we're looking at a point somewhere on this thing. Then what this would be saying is that your gradient has a component along x naught, which is equal to a, and it's got a component along x1, which is equal to b, right? And so the net gradient would be something like that, right? So it's climbing the hill kind of in that direction. And I drew it a little bit sloppy here, but you get the idea. Okay, so a couple of definitions. So basically, gradient descent is all about taking this this output y that you computed. So let's say the output at this point, and comparing it to the known or like basically your annotated minimum value of y, right? And you want that difference to be 0. And you're going to arrive to that again iteratively. Like you want every iteration to bring you closer to 0. There's different ways of computing the difference between your computed and your minimum y. And one popular way to do it is root mean square deviation. So it means let's say y is not just one-dimensional, but it's multi-dimensional. Then you would take the element y's difference between the computed y and the gold standard y, and then square that, and then sum it over and divide by m. So that's just again not really mean squared, but not really root mean squared, but mean squared error, right? So if they talk about mean squared error, they know they're doing this. Okay, and here we're writing down basically the gradient descent algorithm, So we have some x sub n, that could be here, and it's saying that your next attempt at x, or your next guess, is going to be your current guess minus the learning rate eta times the derivative with respect to xn, or derivative of the function at position xn, right? So that should, so you have this derivative, and you're going to multiply that times as learning rate, and you're going to get this, basically this move, right? And that's going to give you your xn plus 1, right? And then again, in multiple dimensions, well, you just, instead of just using derivative, you'll use the multidimensional gradient. And so, if you have a gradient that's pointing up that way, and you want to minimize, in other words, make it negative, then you have to have negative sign with the learning rate. Maybe that'll take you to 2, and then from there, the gradient will take you to 3, and so on until eventually, hopefully, you'll maybe bounce around a bit, and then finally find the bottom, right? And so here you're just writing the gradient descent in a kind of compact notation. Okay. So let's apply gradient descent to the perceptron, and hopefully you'll see where this algorithm for adjusting the weights of the perceptron came from. So let's see. Again, here we have our vector of weights and our vector of inputs. And we said that z is just the sum of x naught times w naught plus x1 plus w1 and so on. And we're going to take the sign of that, but first we're just going to differentiate with respect to just the z part. And we're going to argue that that if y is negative, then that's kind of we're looking for the minimum, and if y is positive, then we're looking for the maximum. And so that's going to give us a sign of this eta, right? Because this eta being negative, that wasn't the case where we're looking for the minimum. If we wanted the maximum, the eta would be positive, right? So again, we want to minimize. We want to minimize. So we're going to take a minus sign in this case. And so we start with some initial value of our weight, and then we're going to subtract the learning rate times the gradient of z. In other words, the kind of the multidimensional derivative of z with respect to the weights. And so the gradient of z is going to be this thing: partial z partial w naught, partial z partial w1, partial z partial w2, right? So what this first term, partial z partial w naught, what's that? Well, I mean, it just means we're going to hold everything else constant. So w1 is constant, so that becomes 0. w2 is constant, that becomes 0. w1 becomes unity, and so all that's left is x naught, right? So partial z partial w naught is just x naught. Partial z w1 is just x1. Partial z wx2 is just x2, right? So as simple as that, the gradient is just the x vector, right? And so that means that your next move is going to be your learning rate times x, right? So you adjust w with this eta times x, and you say, oh, where's the y? There's a y. Okay, the y is always going to be +1 or -1. So in this case, it was -1. So you can think of this as being like a -1. So you could really think of this as being like w plus y eta gradient z, right? It's a negative sign in this case because y has a negative sign inside of it, right? Okay, and so again, if y is positive, then this thing would be plus, or you can express it this way with the y, and then you don't have to think about making a decision. But the point is you get the y, you get the eta, and you get the x, just like we said earlier. Except now you understand where it came from. So this is an illustration of the process of adjusting your weights w. You have some initial guess as to what your w naught and w1 would be, and your desired output is -1. So that means that that if your x naught and your oh sorry, x0 and x1 are both positive, then you want to reduce your w's, right? And so that means that you're gonna move these w's, both of them, in the negative direction. So that means this direction and this direction. So your net direction is going to be somewhere like this, right? Because on W1 its negative direction is this way, and W0 its negative direction is that way, right? That's where it becomes more negative, right? And so eventually it'll drop down and you know, who knows, land somewhere there, and then you'll be converged. Okay, these are just a couple of additional examples of the same thing. Right, and so something that's kind of interesting is that you can use a perceptron to recognize patterns, except it's going to have a little bit of a limitation that we're going to see related to that the fact that it's always +1 or -1, and the fact that it can't be differentiated. There's no intermediate values. So our task is to learn these 5 patterns. So this pattern that you see here is one where you have just +1 in each of these 9 squares. And then you have a pattern here where you have -1 in each of the squares. And this one looks very similar, except this is the problematic one. It's got zeros. Remember, we don't, the perceptron really doesn't work with 0 very well, right? It just puts out plus and minus. So we're going to see how well it does there. And then we have another one here. We have pluses, minus, and plus. And then here we have, again, these things that we don't know what we're going to do with, these zeros and minuses. Okay, so let's look at the first one, this one where it's all pluses. Turns out this worked pretty well, because if we give it a whole bunch of patterns, it'll correctly pick out the correct one as the highest scoring one, and kind of elegantly the one that's most logically the opposite of that, where it's all negatives, that it scores that one the lowest. So this worked out pretty well. Let's see why. By looking at these weights. So basically, what it's doing is it's got a perceptron here that's looking at this square and at this one and at this one and all of these squares, and each of these edges has a weight. So you can think of this as being your x0, or sorry, your x1, x2, x3, and and so on all the way to x9. And these things have your weights: W1, W2, W9. And so take a look at these weights. So like the pattern that you're targeting will have +1 in all of its inputs. So all these, this is 1 times 0.6, 1 times 0.2. So you basically just add up all these, and you're going to see what the output is, right? So let's just do that. You get 0.6 in this column and 0.6 here, and then 1.4. So 2.6. So these add up to 2.6 for the target when you're looking at the target pattern, and their bias weight is -2.6. So these two cancel out, and when you find a target, your result should be 0. Actually, here they said a very, very tiny number, like has to do with basically rounding and the machine epsilon, things like that. But the point is that, remember that you can think of it also as the sine function returns +1 when the input is 0, right? So so when you see this, you should get 0 numerically as your z, and the sine function should return +1, right? And the reason what's kind of cool about this is that it figured out that it wants the sum to be very, very close to 0. In this case, exactly 0. And that way, if even one of these blocks is not +1, let's say one of them is minus, -1, let's say this one, then that would immediately put it into negative territory. Like the y would be immediately become negative. There's nothing you can do to change this pattern without making the y negative, because this bias weight is balanced exactly against the maximum possible score you could get on the from adding up all the inputs times all the w's. Okay, so then we can look at the next pattern, and looks like it was able to that the top scoring pattern is indeed the target one, and the lowest scoring pattern is indeed kind of the logical opposite of that. And if you look at this, then you have, I do the same trick where you add up the columns, you get minus 1.2, minus 2, no, sorry, minus 1.6, and minus 1.8. So together that's minus 3, minus 4.6. So this adds up to minus 4.6 if everything's actually if everything's positive. So actually you would get a plus 4.6, and your bias is minus 4.2. So basically, if all these are negative, -1, this adds up to plus 4.6 minus the bias term. You end up with plus 0.4. So this one is a little bit above 0, but only a little bit. And even getting even one of these to be +1 would mean that, let's say this 0.4 becomes a negative number, this becomes 4.2, and then you are borderline firing or returning a -1. All right. And again, this is rounded off, so you can imagine that maybe instead of 0.4, maybe it's 0.399, right? And so then it would be definitely below 0, and you would be returning false. So this should be actually, again, quite good at discriminating this all negative ones from anything else. Okay, so then we go to the third pattern, and this is all zeros. Okay, this is where it's a little bit more interesting. How did it do? Well, it thinks this is the closest match. So obviously it didn't do terribly well. And if we look at what it thinks is the most distant match, variation on a theme. So it seems to be doing basically nothing. And look at what it got for weights. Here, like 5 of these these weights are zeros. So that means it's basically completely ignoring these 5 inputs. Does that make sense? I don't think it does. But basically what you're saying here is that because these are all zeros, there's never going to be any signal to the perceptron, right? 0 times any weights is always going to be 0. So it's just simply not able to learn this pattern, right? If it had been ones and -1s, fine. But since it's zeros, it just completely messes up. Then we go to this pattern where we have pluses, 2 columns of +1s, and then a column in the middle of -1s. And just like it did in the first 2 cases, it's able to predict this perfectly, or I should say, classify this perfectly. And then the kind of the lowest scoring case is kind of its logical opposite, like its negation. And as you might by now expect, the weights in the middle column, we're expecting -1s, they're all negative. The weights in the flanking columns are all positive, right? So that worked quite well. And then when we tried making it so that the positives are all just zeros, then we had the same problem again, where we basically are able to not do anything here. That seems to be correct, right? At least here for the highest scoring one, we were able to detect one that had the middle column all negatives, but where we're looking for zeros, we simply can't do anything. All right, so that should make clear that there's a serious limitation with this step function in that it could do fine identifying plus ones and minus ones, but it can't really do anything about zeros. Okay. So we're going to stop there, take a little break, and then we'll come back for chapter 3.